Hi everyone, welcome back. Now that we've finished talking about linear ODEs, we're going to move on to nonlinear ODEs. And these are going to be somewhat more complicated, but luckily we're going to have a lot of tools that we've developed as part of both our discussion in the last chapter about ODEs, as well as analogous tools to the stuff we use to analyze nonlinear ordinary difference equations. So let's go ahead and get started by defining what we mean and recalling a theorem from differential equations. So if we have some function f from r to the n to r that is continuous and has continuous partial derivatives. So this is a continuous function and have continuous partial derivatives. And we're going to assume it has all n continuous partial derivatives, so df, and I'm going to use dxi for each of the coordinates, for, of course, I in, not 0, 1 to n. Then there exists a unique solution to the initial value problem. So unique solution to the initial value problem, dx dt, dx dt is equal to f of x, where x of t naught is equal to x naught for any initial value x naught in Rn. Okay, and this is known as the existence uniqueness theorem, or one of the existence uniqueness theorems. Theorem from diffie-q. So you should look it up there. And now let's define a couple of terms that we'll be using. So x of t, a solution, you can also think of as x1 of t, x2 of t, etc., through xn of t for each of the different coordinates. This thing parametrically describes a curve. Describes a curve in Rn. A curve in Rn called the trajectory. Sometimes it's also called a path or an orbit, or path or orbit, because you can think of something moving along in Rn described as a function of time. So this is the trajectory of the system. And it has a velocity. Dx dt. So the standard definition of velocity, how much it moves as a function of time. So pictorially, let's look something like this. So we have, well, let's say we're in R2. So we're in not Rn, we're in R2 here. And we might have some path that goes like that. So let's say this is x of t naught. Maybe here this is x of t1, so some other time, or maybe this is some x of t2, yet another time. And we have some velocity, which is how quickly it's going in each of these directions. Obviously, the velocity changes as a function of time, or it can at least. So let's see, this is here x1, x2. Okay, so now one easy corollary of the existence uniqueness theorem is that you can't actually have two different paths that intersect. And this this is the consequence of uniqueness, because if you had two different paths that intersected, well, then you can prove that they would just be translative of each other. More precisely, let's have the same setup as before. If f is a function from Rn to R is continuous, and has n continuous partial derivatives, zoom back out, df dxi, len the two solutions. So if we have two different solutions satisfying different initial conditions, two solutions x1 of t and x2 of t satisfying dx dt is equal to f of x that have intersecting initial conditions where x1 of 0 is equal to x naught and x2 of some other t naught not equal to 0 is equal to x naught. Len two solutions, let me do this grammatically, must be translations of each other. So x1 and x2 must be translations of each other. More precisely, x2 of t is equal to x1 of t minus t naught. And this proof is pretty straightforward. It's just a matter of pushing through with some substitutions. So let's let some function y of t be equal to x1 of t minus t naught, and let u be equal to t minus t naught. Well, then what do we have? We have dy of t, dt, is equal to dx1 of u, not partial. These are ordinary derivatives. So dy of t, dt is equal to dx1 of u du times du dt, which is equal to dx1 of u du. And when you do the substitution, this is precisely just f of x1 of u, which is equal to f of x1 of t minus t naught, which is equal to f of y of t. Additionally, we also know that y of t naught is then precisely equal to x1 of 0, which is equal to x naught. So by existence uniqueness, y of t is equal to x2 of t. And that completes the entire proof. So basically what this is saying is that if we go into R2 here, if you have some point here, let's start going in this direction, and you have some other trajectory that goes there, then it has to continue on in the same way. So what this is saying is that if you have an autonomous system, so note that this has no explicit dependence on t, which is important for this result, then if that's the case, then you can't have two intersecting paths. One way of thinking about it is that if you go think back to the vector field that's created by this autonomous system, if you're at this point here, well, then you have to choose one direction to go. You can't go in both directions. And so this entire thing is not allowed for autonomous systems. Note that here, one of the important things here is that this f has no explicit t dependence. So this is an autonomous system. Okay. Anyway, moving on from that, now we can give a couple other definitions, which will correspond to the definitions we had for nonlinear difference equations back in chapter 2. And we'll start by defining an equilibrium solution. An equilibrium solution, which is also known as a steady state or a fixed point or a critical point, or a steady state or a fixed point or a critical point, of a differential system, or of the differential system, x dot is equal to f of x, well, this is just a constant solution. A constant solution satisfying f of x bar is equal to 0. Recall that x dot is equal to f of x, and so therefore if f of x bar is equal to 0, what you're saying is that the derivative is equal to the derivative is also equal to 0, and therefore you satisfy your differential system and you're not moving anywhere. And that's also why it's called a fixed point. Note that there's a slight difference here between difference equations and differential equations. With the difference equations, we talked about it in terms of repeated application of some function. Here, instead, we're talking about things that a function that is equal to the derivative of your x function. But this is just the standard difference between discrete and continuous, the discrete and continuous worlds. Okay, what else do we have? Well, we already started talking about stability in our section on, in the last chapter when we were talking about linear systems. Of course, we can apply the same kind of thing to nonlinear systems, but instead of things being globally or locally stable or asymptotically stable or unstable, here we also have two different concepts of local versus global stability. So let's talk about local stability first. And I think global stability will be in a different section. But so an equilibrium system is locally stable. And this definition will exactly match the definition. So you should compare this against definition 2.3 from chapter 2 for difference equations. But anyway, an equilibrium solution is locally stable if for any epsilon greater than 0, there exists some delta greater than 0, such that every solution x of t of x dot equal f of x with initial condition x of t naught is equal to x naught. Well, what we have is that the distance, we're going to use the Euclidean distance here. It doesn't matter so much, but in this class we're always going to talk about Euclidean distance, so this is the 2 norm. So if the initial point is less than, the distance of the initial condition from our equilibrium is less than delta, then what we have is that the distance of the trajectory, so x of t, from that equilibrium never gets further than epsilon. So basically, if you start close enough to your equilibrium, you never go too far away. That's what it means to be stable, and otherwise it is unstable. Yeah, so the basic idea is, again, if you start close enough, you don't go too far away. Let's give another definition. So this is 5.3. We're going to talk about local asymptotic stability. So in the case of linear equilibria, which are just 0 unless you have a degenerate case, we talked about things asymptotically approaching 0. Well, for local asymptotic stability, we just mean that it asymptotically approaches the equilibrium point wherever it is, which doesn't have to be 0 anymore. So an equilibrium is locally asymptotically stable. Locally asymptotically stable, well, if it is first locally stable, otherwise we don't call it stable at all. So if it's locally stable and there exists some gamma greater than 0, such that if you start off within distance gamma, then the limit as t goes to infinity of the distance between x of t and x bar, our equilibrium. So that distance has to be equal limit to 0 as t goes to infinity. So pictorially, what we have here is, well, if you have some starting point and you have some distance gamma, let's see if I can draw a circle. You have some starting point, you have some distance gamma, and local asymptotic stability means that if you start within that distance gamma, then you'll always eventually go to your point. So this is local asymptotic stability. Whereas if things are stable, that isn't quite as strong, because all you're saying is that if you start again at some point and you have some circle of distance delta around here and some other bigger circle of distance epsilon, well, then if you have a point that starts within your distance delta, it might bounce around out here, but it never leaves that bigger circle. But it doesn't necessarily have to approach the equilibrium point. It just has to stay not too far away from it. Okay, so these definitions are almost exactly the same, except you've translated it from the discrete setting to the continuous setting of the definitions we saw in chapter 2. The next definition is a little bit trickier, but it's the natural generalization of periodic solutions from the discrete case to the continuous case. And so in the discrete case, we had this idea of how many times you've applied your function. Well, here, because things are continuous, we don't have the sense of reapplying a function over and over again and iterating. Instead, we just have things moving continuously through space and time. And so because it's moving continuously in time, we instead talk about periodic solutions as having some period before they return to the starting point. So a length of time instead of a number of iterations. So now a periodic solution, to be a bit more formal, is a non-constant. A non-constant. You could think of a constant solution as periodic because it's always in the same place, but that's not a very interesting definition. So a periodic solution is a non-constant solution satisfying x of t plus capital T is equal to x of t for all t on the interval of existence. Well, so basically all the times in which the solution exists. As you recall from differential equations, sometimes your solution doesn't exist for certain parameter ranges, for certain ranges of time. So on the interval of existence, for some non-zero time, for some capital T greater than 0, and the minimum T for which this is true is the period. So obviously, if you have a period 2 pi, well then you still return to your original point after 4 pi, but you're not going to call that the period. And let's go ahead and give a very concrete example, just so that we all are on the same page. So let's say we had a system of two different differential equations, dx dt is equal to y, and dy dt is equal to x, and x of 0 is equal to 0, and y of 0 is equal to 1. So you know how to solve this. I'm not going to solve it here, but when you solve this system, what you end up with is that x of t is equal to sine of t, and y of t is equal to cosine of t. So you'll notice actually that this is a linear ODE, but we do get this periodic behavior even for a linear ODE. You'll notice that in terms of the classification, what we have is a center here. It is a neutrally stable center. And if you draw this out, there are two different ways to draw it. One way of drawing this out is to draw it on the t-axis, and you draw out both x of t and y of t. Well, when you do this looks like, let's see, I went 3 up. Well, this looks something like this. And so this is x of t, since it's just a sine wave, and y of t is a cosine, so it's this And what you'll notice is that these are sine and cosine, and so you have a period of 2 pi. And what you'll notice is that after a period of 2 pi, it repeats itself, which is sort of the point of many of these sines and cosines, of sine and cosine. And if the other way of drawing it is to draw it in the phase plane, so you have x and you have y, and so they're two different coordinates. And what we have instead is we have a circle that goes around. If I can draw a circle, that's not a very great circle, but you get the idea. And so the trajectory is it's a parameterized curve that's going around and around in circles, and after a time period of 2 pi, it repeats itself. So just a fun fact, autonomous scalar equations cannot be periodic. So you need at least 2 equations, unlike the case of difference equations. And this is something this is something we're going to prove right now. So this is theorem 5.2. And the idea is that autonomous scalar equations can't be periodic. So let's be a bit more precise. Let's assume we have some function f from R to R, which is continuous. Well, then x dot equal to f of x has no periodic solutions. Okay, and let's prove this now. And we'll do a proof by contradiction. So we'll suppose that suppose x of t is a periodic solution with non-zero period, with some period t greater than 0. Okay, so we're assuming we have some solution, and of course we know that dx dt, so dx of t, is equal to f of x. That's by assumption. And what we can do is we're going to multiply by dx dt on both sides. Now this might seem a little bit weird, but what we end up with is dx of t over dt squared is equal to f of x times dx dt. And now we have that, let's try taking the integral of both sides. So if we take the integral of both sides from t to t plus t, capital T, well, this here is some integral of dx dt squared. And we're going to integrate this, the variable inside of the integral is f. I'm going to use s for that. So dx of s, ds, etc. And let's integrate the other side using the same limits of integration and the same variables. So this is going to be f of x times dx of s ds ds. Okay, and so now we're going to focus on solving the right-hand side. So we're going to let u be equal to x of s. And then this right-hand side is going to be equal to the integral from x of t to x of t plus capital T of f of u. Come on. F of u du after that change of variables. But now, what you'll notice here is that this quantity is greater than 0 because it is not identically 0, because we assume that it's not constant, not identically 0. However, this quantity here is equal to 0 by periodicity, since it goes back to where it started by I'm doing this in red, by periodicity. And of course, that implies a contradiction. And therefore, x of t can't be a periodic solution. And that completes the proof. Okay, so that proof was a little bit too slick to really get a good intuition for it. So instead I'm going to draw out the intuition a little bit differently. So if you think about it, what you have is you have some x-axis, and you have some, and then we can draw over here, we can draw x dot, so the derivative, and then you have some function, f of x, which is equal to the derivative, of course. So let's say it looks like that. And so now, whenever the derivative is positive, well, then you're going to go up, right? That's sort of the idea of the derivative being positive. You're going to go up as time goes on. When it's negative, you're going to go down. And when it's positive, you're going to go up. Now, when we were doing this with difference equations, you could skip over an equilibrium and it could bounce back and forth. But because everything is continuous, you can't actually skip over any points. And so you end up like just getting pushed along it until you hit an equilibrium or not. And so you can't actually have any sort of periodic behavior with just a single dimension. You need this two-dimensional setting up here where you can actually go around. And so in this way, difference equations are actually a little bit more complicated than differential equations, because with differential equations, you don't have this possibility of jumping around the way you do with difference equations. Okay, so now that we've done that, let's talk a little bit about stability of nonlinear equations. And we're going to first start by giving a first derivative test. So suppose f prime suppose the derivative is continuous, it's on some interval, continuous, and x bar is in I, where x bar is an equilibrium of x dot is equal to f of x. Well, then we know that x bar is locally asymptotically stable, if the derivative at x bar is less than 0, and unstable if the derivative at x bar is greater than 0. And for those cases, we're going to give it a special name. We're going to again call this hyperbolic. So definition 5.5, x bar is hyperbolic if it's not equal to 0. If f prime of x bar is not equal to 0, and f prime of x bar is called the eigenvalue, value of the linearized system, linearized equation at x bar. Okay, and this is basically just a natural consequence of the results that we talked about for the linear systems in chapter 4. And what we basically do is we look really, really closely around an equilibrium, and if you look really, really closely, then it's almost linear, and so then you can use all the same results of a linear system of equations. And it turns out that when you do that, you end up with a matrix again. This will end up being the Jacobian when we go to higher order differential equations. When we go to higher order systems of differential equations. But for just a single differential equation, a first order differential equation like we have here, the Jacobian matrix is just the first derivative. And so the first derivative test for this is just, well, if it's less than 0, then it's locally asymptotically stable. And if it's greater than 0, then it's unstable. Now, when you generalize this to higher dimensions, you need to be taking the real part of it, and whether that's less than 0 or greater than 0. But of course, you don't need to worry about that so much when you only have one dimension. And so in the next couple of videos, we're going to talk a little bit more about local stability and generalizations of it, as well as possibly give some examples of biological systems where you can apply this sort of local stability analysis, even though they're systems that are much harder to solve because they are nonlinear ones. So I will see you in the next video.